Hello everyone, welcome to this tutorial on MLIP's Machine Learned Interatomic Potential. And the MLIP which we will be looking at today is called MACE. So MACE stands for Message Passing Atomic Cluster Expansion. Okay, so atomic cluster expansion is a framework in which you express energy of a crystal structure in terms of atomic basis, and MACE combines this form of energy expression with the graph neural network to produce an MLIP which can predict energies and forces. So in this tutorial what we will be doing is we will be training a MACE model from scratch using ab initio molecular dynamics data set, and we will use this trained potential to simulate and do some molecular dynamics simulation and see how they are looking or how the energies converges when we do simulation at high temperatures. Okay, so we will start by once you have set up the MACE environment, you activate the MACE environment and then you go inside and once you see the directory, so you can see the files inside the directory, and now you import the necessary packages. Okay, and once the packages are like imported, you go on to downloading the data set. The data set is silicon data at 800 Kelvin, and each cell consists of 64 atoms. Now we will try to visualize this data set using atomic simulation environment, ASE. So just check one of the entries of this data set. So this is like 110 configurations in this data set. Okay, and we will check one of the entries, the entry 0. So it's Si 64 atoms, and the cell dimensions you can see as 10 10 10. It's a cubic cell with each 10.8 angstrom as one of the dimensions of the cube, all of the dimensions of the cube. And there is a visualization module in ASE which you can use to visualize the structure in 3D. You can rotate it and see it. It's all silicon atoms with 10 by 10 by 10 cell. Now what we do is take this ab initio molecular dynamics data set at 800 Kelvin and split it into test and train. Okay, so what this data set has is various configurations of this Si64, and corresponding to those various configuration, the energies. So what we are trying to map, what we are trying to learn using this framework of MACE is the relation between the configuration and energy of a given crystal structure. Now once you have like split the data set, you save the train data in sitrain.xyz file and the test data on sitest.xyz file. Now what we will try to do is we will try to train MACE. Okay, so we first specify the outputs directory where we will be storing all the outputs. Okay, and now comes the hyperparameters that we want to specify, that will specify our model architecture. Okay, so initially we start with this model naming. We will name it SI, and we will specify the directories where we want the model to be stored, the log of the runs, the checkpoints and the results. Okay, and we give the path to the training file, and inside the training file the key to the forces. So the data set has forces under this column named as forces and energies under this column energy. So we have to provide the keys. It may vary according to data set. You have to check the name what are given in the data set. We then give the path of the test file. Okay, and we followed by the hyperparameters which define the model architecture. So there are various types of models. So there is linear MACE, there is MACE, there is dipole MACE. You can all check out in their website. We will be using the vanilla MACE. It's called which we call by this name MACE. So next hyperparameter is number of channels. So this number of channels will determine the dimension of the embedding vector. That is, when you have a graph neural network, you will have the features, chemical features in the form of a vector. It specifies the dimension of that vector. Rmax specifies the interaction radius. So in this framework, cluster basis functions are made, and this Rmax will tell you the cutoff up to which to consider clusters and make the cluster basis function. Max L specifies the level of features that you are including. So in this training that we will be doing, we are taking max L equals to 1. So L equals to 0 corresponds to scalar features. L equals to 1 corresponds to vector features. L equals to 2, 3, 4, all of this like refers to each of the tensor features. So you can capture higher order features, okay, just by tuning this L, max L. For this tutorial, we will be considering only scalar features and vector features. So number of interactions, it's a message passing neural network. So we keep the number of interactions as 2. That means just message will be passed between neighbors and neighbors of neighbors. Okay. Correlation. So correlation is the body order. So think of the types of interactions that we are able to capture using this atomic cluster expansion. Okay. So you can have like single body terms, which is the atom itself. Two body terms when you have two atoms connected by bonds. Three body terms when you include the angle between the three atoms. Okay. So just like that, you can keep on increasing the body order of interaction so as to capture higher geometric features, okay, into your model. And this max L is the angular resolution. Okay, so it's set at maximum, which is 3. So it's the precision with which the angular resolutions are captured. Okay, so think of perovskites. So they can have cubic structure or the tetragonal structure with very finer angular displacements of the central atom. If you have higher angular resolution, those small displacements will be captured correctly. Okay, so here we are setting it at max resolution. So these three parameters, the number of interactions, correlations, and max L, these are all set to their recommended values as recommended by the developers of MES. Okay, and then we have the optimization run, that how the weights and biases will changes during the training. So validation, we will use 5% of the training data for validation. Batch size is 10. We will train the model for 15 epochs. Data type is float 32. We will be using CPU for training and a random seed of 1 to 3. And all these parameters, we will save it to an YML file and later call this YML file during the training run. So as to summarize the parameters, we have a moderately sized network which is with 64 number of channels are 64, which denotes the dimension of the embedding vector. We are including fairly short range interactions with all are within 4 angstrom and not more. We are training an equivariant model with scalar and vector features. We are not considering any tensor features. There are two interaction blocks, which is here it refers to the message passing. So each atom will get updated of its neighbors and neighbors of neighbors. Okay, and no more, just 2 layers of message passing we will be doing. And we are capturing up to 4 body interactions, which is given by this correlation. Correlation 3 means body interaction is 3 plus 1, which is 4. And we are setting at high angular resolution, which is denoted by this max L equals to 3. Now let's start the training process. So once training is done by this function, which is MES run train main. Okay, and to this function we pass the input.yml file, which denotes the parameters which I have just now specified, which will dictate the architecture of the model. Now once you start training, okay, you will see after each epoch happens, you will see the losses, the RMSE, and you will see 2 RMSEs, one on RMSE on energy per atom and RMSE on forces per atom. Okay, so after 15 runs, we have done till up to 15 runs. Once it's done, the model is actually saved. Okay, so let's check the output directory. and in the output directory our model is saved with the weights of the results of the 14th epoch, and we have the run logs all saved. Okay, now just we want to take a look at the individual data points of how it like what happened in each run. So you can see the time steps and the losses. Okay, and you can do a transpose of this data frame, and this way for each epoch you have all the information. You have the MAEs, you have the RMSEs. Okay, for each of the for each run of the training run, each epoch of the training run. Now let's try to plot this. It's easier to visualize in graphs than to visualize in tables. Okay, so if we plot this, what we see is the training and the validation loss with the number of epochs. So at the end of 14th epochs, both the training and validation loss has actually converged. Okay, and now we have a trained model based on the AIMD silicon dataset. So we have a trained potential ready. Okay, so now that we have a trained potential, let's try to do molecular dynamics using maze. So what we will do is we will use the maze calculator, which is in this AAC in the atomic simulation package. Okay, and we will just take one of the structures. So we take the index 0 structures, like one of the configurations we take from this test file that we have defined before. So we are taking one of the structures in the test set and not in the training set. And now we import the maze calculator. Okay, and initialize the model that we have trained, the name of the model. Okay, and inside this maze calculator goes our potential. So the we have trained the potential. We are giving the potential as to the back end of the calculator. Okay, and the calculator will use CPU with default data type as float32. And now we will be doing an NVT ensemble molecular dynamics, which is given by this function simplemd, and we give the initial structure, the final temperature up to which we want to do the molecular dynamics simulation. We initialize the name of the calculator, the maze calculator. So the calculator has at the back end of the calculator is our trained potential, and we are giving the molecular dynamics this calculator. And the frame names will be saved in this format. So the simulation will run for 500 steps, and the data will be stored or plotted for every 10 steps. So now if we run this block, so you can see after each 10 steps is printing 1 point, and this is how the molecular dynamics is actually evolving with time. So what's happening is this simplemd at the back end of the simplemd function, how it works is the initial velocities and the forces are actually initialized with based on Maxwell-Boltzmann distribution. So at 300 Kelvin. So if you look at the Maxwell-Boltzmann distribution at 300 Kelvin, you will see a distribution of velocities. So that's how you initialize your initial structure, and how it evolves is based on something called Langevin dynamics. So Langevin dynamics is a classical differential equation to define evolution of a particle. It's a differential equation that will say how particle evolves in time when it is under a potential and there are thermal fluctuations. Okay, so the temperature will rise from 300 to till 800, and we are running 500 MD steps in 500 steps. Okay, now let's see how it evolves. So it's still evolving. We are above 400, reaching 500. So the fluctuations in temperature that you see, it arises from the fact that temperature is not directly calculated. It's actually taken from the kinetic energies. Now kinetic energies have a whole distribution, and there is a friction term that is in the Langevin dynamics that dictates the damping, and there is also this thermal fluctuations that denotes the energy entering the system. So energy is not actually constant. Okay, so as the temperature fluctuates, you can also see fluctuations in energy. So if you run this MD for like more steps, okay, and with a better trend potential, you will see convergence in temperature and energies with time. Okay, yeah, so this is the result of our simulation. This is the result of our molecular dynamics simulation based on the potential that we just now trained on the AIMD silicon data at 800 Kelvin. Now, apart from this force field, so maze comes with other foundational force fields that are pre-trained by the developers. Okay, so these force fields are trained on large data sets. Okay, and we can use them directly out of the box without any further training. Okay, so let's try to do one molecular dynamics on the same structure using one of the Maze's foundation models. So first we initialize the structure from the test data, same index 0 structure we will take. Okay, and from Maze calculators we import this Maze MP. Okay, and the Maze MP Maze calculator, we call this Maze MP function, and it will run on CPU with this default data type as float32. Similarly, we again call this function simple MD. The inputs to this will be the initial configuration, temperature. This time the calculator is the Maze foundation model and not our trend potential. Okay, and the data will be saved in this, and again we will run it for 500 steps and print every 10 steps. So let's see how this evaluation runs. Yeah, it's done. Now this completes our simulation till 500 steps of a max temperature up to 800. It can go up just because of the fluctuations in kinetic energy. Yeah, so that brings us to the end of this. So what you can do is visualize the trajectory of how this evolution of energy happened, like how the atoms fluctuate during this evolution of these 500 steps using this software called Ovito. Okay, so given in this notebook are the instructions to download Ovito and the instruction manual. So you can use the XYZ file generated from this Maze training, load it to Ovito, and you can play the animation and you can see how it evolved through these 500 steps. So that's all for this tutorial. See you on the next tutorial. Thank you.